I will talking about a network model of the appearance of biologically irresolvable conflict in prehistoric hunter-gatherer groups.
So is it your research program?
No, my lab crashed in the morning, and
No, I mean like what's the studies? What are you studying?
Your background.
Okay. My background?
What is it? Facultad de...
Okay. The Faculty of Science of the UNAM. This work is with the Dr. Tom Freud.
So he's a bachelor student.
In this case, we use a new type of social network, social model, that with the name of REDS. REDS it's a model proposed by Antononi and Seth Bullock in the 2014. This network it's a social model that puts n number of nodes in a random position in a plane, and then the network starts to try to create connections between the agents. This model has four principal features. That is the social energy, the social reach, the synergy, and the distance. The social energy is the energy for doing connections between agents. The social reach it's a constraint or a limit for doing the connections. That is the maximum distance between two nodes for doing a connection of the two nodes. The synergy it's a parameter for improves the connections or reduce the cost of the connection. Every edge in the network has a cost. The cost is determined by the distance between the parameter of the synergy plus is multiplicado.
No, es más.
How did you say multiplicado? Times. Times for the number of neighbors that the two nodes share. The REDS models a lot of behavior of a society. For example, the REDS has what did you say? A large number of connections, a clustering patterns. For example, in this is a cluster, another cluster, for example, and model the correlations between the agents or the interaction of agents. Well, for some background of the experiment, we need to know what is the Dunbar's number. The Dunbar's number it's a number proposed by Robin Dunbar, and this number means the maximum capacity for humans for doing social connections with other humans. This number is around 150. That is the maximum number of personal connections with other people. All the humans has a capacity for doing connection or for relation with other humans, because the humans has a limit for our memory, our, how did you say, by recuerdos,
Memories?
by memories, because we need to
Associate?
no, recordar.
Remember?
We need to remember the information of a lot of people, and we can remember the information of the, or the, how do you say, the behavior that we need to do with, for example, a friend, or for example, an assessor or a teacher. It's not the same behavior or the same relationship. Sorry. And we need to remember the memories with these people, these guys. In this experiment, we use a topology of the reeds. We generate a reeds topology, and then we run a traditional hotbit network over on the reeds topology for proofs if the Dunbar's number is correct. The cooperation in the small populations are all around to 100%. That is, all the nodes converge to the same stable pattern. That is, all the nodes cooperate in the same attractor. I don't know. all the nodes converge to the same color, to the same state. In Dunbar's proposed 4 types of population: 5 people, 15 people, 50, and 500 of humans. And in 5, 15, and 550 elements in the network converges to the same pattern with less energy, with the original energy, with the original social energy, and with a double energy. That is, the cooperation in small groups, it's better, or is totally. But we saw that, for example, in 150 nodes, that is the Dunbar's number, we can see that a few number of nodes turns to other pattern. Some of these nodes doesn't converge with all the community. That is, the Dunbar's number is correct, because around the 150 elements, we start to see some humans doesn't cooperate with all the population or the community. When we increase the number, if you can see, the cooperation broke totally, because the conflict resolution is for cluster, not all the community. For example, in this cluster, the nodes goes to a same pattern. In this, it's another pattern. For example, in this cluster goes to red, in this blue, and all the resolution conflict goes to start in a social group, in social groups, not in all the community. Sorry. I need to represent the strength of the connections. The green connections are weak connections. Blue connections are the medium strong connections. The red connections are strong connections, and the black connections are the very strong connections. If you see, in the 50 nodes, all the connections are black. That is very strong connection. In 5 and in 15, all the connections are black, and it's a complete graph. All the nodes connected with all the nodes. But, for example, in 500, if you see, the strong of the connections reduce a lot of, because the major of the connections are blue or green. With this approach, the number was correct because around of 150 individuals, the network doesn't converge all the nodes to a stable pattern. Some nodes around the 3 or 4% goes to another pattern. That is the start of a conflict in a population. And when the professor Tom and me finished the experiment, we saw that that in these networks, the social energy of the nodes has a relationship with the capacity of convergence or the cooperation. For example, in the population of 5 nodes and 15 and 50 nodes, doesn't matter if the energy is in the half or in the double. But for example, in the 150, that is the numbers number, with the double energy, all the nodes converge. But with the original energy, the 97% around converge. 3% doesn't converge with all the rest of all the remains community. And with the half energy, we saw a 70% of cooperation. If we improve the number of the population, doesn't matter if the energy is going to the double. The cooperation turns around the 58%. With the original energy turns to 53%, and with half energy it's around the 51%. We show a reduction of the cooperation if we decrease the energy and augment of the cooperation if we improve the energy. And we saw the inverse relationship for the strength of the connection. For example, in 5, 15, and 15 nodes, all the connections in the graph are very strong. But in 150, the strength of the connection reduced a lot because in the very strong connections to around the half of the total of the connections, and the weakest connection tends to increase his number, and in 500 nodes, the very strongest connections are the less of the connections. In the population, we saw a behavior of reduction of the strongest of the connections, and the time of computational times in 150 turns very exponential because we see, for example, in this graph, that the number of the connections turn to not a complete graph, but a graph with a high degree of connections. Dunbar thinks that in a 150 population, it's the optimal number for doing a social group because the degree of the interaction are very high, but starts to having some problems to cooperate with all the agents. And the conclusion is we show a correlation between the social energy of the network and the capacity of cooperation, and we saw an inverse relationship between the size of population and the strength of the connection. More size, less strength. That's all for me.
Okay.